Hey physics students, welcome to another edition of Rapid Review for Honors Physics. Today we're going to be talking about impulse and applications of impulse for your safety. Let's think about an example here where you are driving your truck into a brick wall. Okay, maybe you might choose to drive your truck into a hay bale instead. Which one would you prefer? Of course, you're preferring the hay bale. Let's analyze why that's true, right? If you're starting out with a velocity of 10 meters per second and ending up with 0, you're going to have a certain change in momentum. That's the mass of your truck times -10. Or if you drive into the hay bale, you're going to be having the same change in momentum, which is -10 times the mass of your truck. So the change in momentum in both cases is the same. Now, if you want to ease the force on you, you can take advantage of your knowledge that even though you're stuck with reducing your momentum by an amount equal to the mass of the truck times the velocity change, which was -10, even though you're stuck with that change in momentum and therefore stuck with the same impulse requirement, you can choose how you want that impulse applied. Maybe you want the impulse applied over a long period of time so that you never feel much force. And of course that will be your preference if you would like to most comfortably survive that crash. Okay? Now that knowledge is used in real life. I'd like to credit in these photos here my colleague, Mr. Burns from Westford Academy, and he took pictures of various safety devices on highways nearby. Just driving around, you can see things like this. This is called a Fitch Barrier. Who knew it has a name? That's a Fitch Barrier. And it's there so that when you hit that thing, you won't stop short. You'll kind of skid it or slide it along the pavement and slow down gradually. So it lengthens the time so that your impulse, which is your change in momentum, is going to be, I'll remind you they're vectors, force times time. We have a big time, so there's a little force. That's the purpose of these safety devices, and that's why you see them. They're not just for visibility, they're for your safety. If you look down at this aerial view, it's a little weird here. This is just a shadow, but you're looking down at a cell phone tower that's here, and you can see various Fitch barriers lined up. In real life, it looks more like this. Okay, so that is right out of Google Maps from near Route 495. If you're from out of town, you can look for this just north of the Route 117 intersection with Route 495 interstate. That's I-495. For those who like to call their interstates like that. And it's right near the Candy Mansion. More on that later. Okay, so here's another example, guardrails, right? You can put in a rubberized piston. I'm going to change colors here. I think this green's not working for me. This rubberized piston so that when you crash into it, right there, it's going to collapse and crush a little bit so that you don't stop short. Another way to change your momentum is to change your direction, right? So your momentum can be a change in direction or a change in speed, as you know, because it's a vector. So sometimes we design things so that as you're driving, you might drive right up that guardrail, or you might, that's why they bury the end of it, or you might get deflected to the left here if you run into that by accident. So the idea of all of these safety devices is to lengthen the time so that you have less force for a given change in momentum. Okay, there's more here. I skip some of these slides here. I'm going to skip right here to a problem involving a change in momentum of a ball hitting a brick wall. And we compare case A, where the ball sticks to the wall, and therefore we have a final velocity of 0 meters per second. We're going to compare that to case B, where it actually bounces off and has a final velocity of 28 meters per second. Be careful! The velocity is shown there as 28 meters per second, but you know it's negative, right? Because the arrow points to the left. Your perspective, that's the left, right? The arrow points to the left, so you want to make sure that when you solve this problem, you use negative 28 for the final velocity. And if you do that correctly, you'll find out that, did I put the answer here? I didn't put the answer. We'll do that in our heads. The final velocity, or the change in velocity, is negative 58 meters per second. That's the velocity change. Here, of course, it's negative 10. So which has the greatest acceleration? Ooh, it's a little quirk of this problem. You have to assume in both cases the time of the collision is the same in both cases. So just make that assumption. I'm not sure that's a great assumption either. It's something I don't like about this problem. But it's good to be thinking about these kinds of things because they remind you that change in momentum is a vector, and you have to consider the pluses and the minuses. Ah, yes, the Candy Mansion. I looked this up. You can research this too. It's in the town of Bolton. It still exists. It's a landmark for those in the area as you come down Route 495. Southbound, you will see this just before you get to the Route 117 exit in Bolton, Massachusetts. And that's all I have to say about the Candy Mansion, and that's all I have to say about safety devices that take care of impulse change by lengthening the time in the impulse. Tune in for another episode. We'll be back soon.